Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our fourth set of notes with Chapter 3 that deal with understanding how you interpret somebody else's measurements to know how many significant digits that they've got. So when you make the measurement, it's easy for you to understand what were your certain digits and where was your estimated digit, and therefore how many of the digits were a valid part of your measurement and not a placeholder. But that's different than when you're actually looking at somebody's measurement. So how do we know when we write a measurement or when we look at somebody's measurement, how we should write the number so everybody interprets it in the same way? Well, what we do is we follow what are called the significant figure or significant digit rules. Now, first rule is a very simple one. Every non-zero is significant. So if I'm making a measurement and I write down numbers that aren't zero, they were always a valid part of my measurement. They're not just placeholders to tell me where the decimal is. So if I write down 123.2 grams, I literally mean every one of those digits was a valid part of my measurement. So that would have four significant figures. Now, remember when you make a measurement, the digits you put at the beginning are our certain digits. They're the ones that everybody would put the exact same thing. So we definitely knew it was more than 100, less than 200, more than 20, less than 30, more than 3, less than 4. The 123 part, the 1, the 2, the 3, those would all be our certain digits. And our last digit we wrote down, which was the 0.2, is where our estimate came in. So when you're writing a measurement, you have the certain digits and the estimated digit. And the last significant digit would always be our estimated digit. So in this case, every single one of those would have been a valid part of our measurement. And the tenth spot where that 2 is where our uncertainty or our estimation is. So think of it as 123.2 plus or minus zero point 0.1. The true value is somewhere going to be between 123.1 and 123.3. That's literally what that measured value would mean. So that has four significant digits. So when there are non-zeros written, they were always a part of the measurement. The only things that really have to watch out for are zeros. Because as you saw with the two graduated cylinder situation we looked at, sometime a zero was a measured part of the value, a measured part of the measurement and was, either a certain or an estimated digit. And sometimes zeros are there just to tell you where the decimal is. So zeros are really what the next three rules, which are the important three, really they help us interpret how we handle zeros. So zeros between non-zeros are always significant. So always means every single time. So whenever we have zeros between non-zeros, like in 1004, if the 1 was measured in the thousands place and the 4 was a non-zero, so it was measured in the ones place, then all the zeros in between had to be measured certain digits in this case. So it was definitely bigger than 1000. It was definitely 0 hundreds and 0 tens, and it looked like it was around 4. So this would have four significant digits. So zeros between non-zeros are going to always be significant. So this would have four significant digits, and that 4 is where my estimate or uncertain digit is. So it's like 1004 plus or minus 1. Somewhere between 1003 and 1005 is where the true value of that measurement is. Now, next we can also have zeros at the beginning of a number. Zeros at the beginning of a number are never, capital N-E-V-E-R, never significant. So these are the ones that we just never count. So if I write 0.01 grams, obviously that first zero before the decimal point, you don't even have to write it there if you don't want to. So obviously that is a non-significant digit. Well, since the next zero is also before our first non-zero, then that next zero also has to be something that wasn't measured. It was only there to show us where the decimal is. Because if we get rid of that zero right here, we're obviously going to change the number. 0.01 is very different than 0.1. So zeros at the beginning are always about showing where the decimal is. So they wouldn't have ever been a part of our measurement. They would have only gone to show us where the decimal is. So in this particular case, we only have one significant digit. So 0.01 doesn't have many significant digits. And the estimated digit has to be our last significant digit. Well, since the first two zeros didn't count, our estimated digit would be our only significant digit, which would be the 1. So this really only has one significant digit. So this is like 0.01 plus or minus zero point 0.01. That's a number with a huge amount of uncertainty. So zeros at the beginning never count. Zeros in between always count. And then finally, what about zeros at the end of a number? Well, the rule here goes, zeros at the end of a number are significant only when a decimal is shown. And this is something we looked at with the two graduated cylinder situation. So hopefully you have a basis for understanding why this would be true. So we have a number like this, 12.00 meters. Both of those zeros are at the end of the number. Now remember, It's not zeros at the end or after a decimal point. It's zeros anywhere at the end of a number. Have to count if there is a decimal shown. And there is a decimal shown after the 2. So this means both of those zeros also are significant. So this would have a total of 4 significant digits. And literally what this would mean in terms of a measurement is I'm certain about the tens, I'm certain about the ones, and I'm certain about the tenths. And it's about 0 100ths. So this would be like 12.01, or I should say 12.00 plus or minus 0.01. So our true value is probably somewhere between 11.99 and 12.01. And that last zero would be where our last significant digit is. So this would have 4 significant digits. Now, if I write 1200, now we're talking about an entirely different number. It just has to have the same digits, 1s and 2s and 0. But 1200 is obviously not 12. Well, if I have 1200 with the decimal point put after the 0, same thing. These are zeros at the end of the number. Those zeros both come after my last non-zero, which is the 2. And there is a decimal shown somewhere in the problem, so these zeros also have to count. So this also has 4 significant digits. Now, this would mean 1200 plus or minus 1. So that would be my last significant digit, is that final 0. Since both zeros counted, the last significant digit would be the last 0. And this would mean like 11 or 1199 to somewhere between that and 1201. The true value would be somewhere in there if we have 1200 plus or minus 1. So my estimate was in the ones place this time. Well, what happens if I write 1200 without the decimal point? Now those are zeros at the end of the number. There is no decimal point shown in the number, so therefore I have to say neither zero is significant, and this would only have 2 significant digits. So this would mean that 2 is my uncertain digit. So this would mean 1200 plus or minus 100. So the true value is somewhere between 1100 and 1300. That's where the true value would fall. So this is a much less precise number. Well, it should be if it's plus or minus 100. It should be much less precise. So zeros at the end only count if there's a decimal. And now at this point, usually somebody in the class will say, well, what happens if we want 1200, but we want to have 3 significant digits? We want this 0 to count, but that 0 not to. So how do we do that? Well, really, there's only one way to do it. And you already know the technique, you just didn't realize you could use it in this situation. If we write 1200 in scientific notation and put a 0 on the end, now that would be 1200 with 3 significant digits. Because the 0 is at the end of the number, there's a decimal point shown, so that means the 0 counts. So that has 3 significant figures. And it literally means 1200 plus or minus 10. In the tens place, which is really where that 0 is, so I've got 1200 and I lopped off that 0 and said it wasn't significant. So 1.20 times 10 to the third is still 1200. That's exactly what it equals. But now that 0 would count and that 0 wouldn't. So this would be 1200 plus or minus 10. So it would be somewhere between 1190 and 1210. So the true value would be somewhere in that range. So that's how we would make one 0 count but not the other. The only way to do it is to put it in scientific notation. And then I can just put how many zeros I really wanted to count. Now our last rule doesn't deal with zeros. So we've got the 3 rules with zeros. Zeros at the left never count. Zeros in the middle always count. Zeros at the end count if there is a decimal. So what happens in other situations that we might run into? Well, that's where Rule 5 comes in. These handle the other types of numbers we're going to see in chemistry. Counting numbers and defined quantities have an unlimited number of significant digits. So those are words, but what do those words mean? Well, first, a counting number. Let's say I have 3 gold atoms, or 3 pencils, or 3 of anything I'm counting, 3 cars. Well, I either have a car or I don't have a car. I have a person or I don't have a person. I have an atom or I don't have an atom. So when you're counting numbers, you don't really have any uncertainty in your counting. I mean, if it's a valid number and you counted right, you mean exactly 3 gold atoms. So when we say something only has 2 or only has 3 or only has 4 significant digits, we're actually limiting the significance and the precision of that number. Well, if we have a perfect number like exactly 3, we literally mean an unlimited number of significant digits. So it'd be like 3.00000 forever is really what I mean with a counting number 3. So it wasn't measured. I didn't have an estimated digit. It was exactly 3. So counting numbers have unlimited significant digits. You could, if you want to, instead of writing out unlimited, you could use the infinity sign. That would work just as well. Now, what's a defined quantity? Well, we know that 1 hour is 60 minutes. It's not around 1 hour equals around 60 minutes. It's exactly 1 hour equals exactly 60 minutes. So these are defined as exact numbers. They're not measured numbers. They're not around. They're exactly. So in this case, the 1 and the 60 in that defined set of quantities means exactly. So once again, they're unlimited in significance. So 1 hour equals 60 minutes. The 1 has an unlimited number of significant digits, and the 60 has an unlimited number of significant digits. They're kind of like counting numbers in that they are exact numbers. So basically, every time you see a number, you should be able to apply one of these 5 rules to understand how many significant digits are in that number. And we're going to turn around tomorrow and use that when we do math to figure out exactly where we're going to round to. So we'll be coming back to this and using this routinely every time we get out our calculator. Now, let's practice it a little bit. Well, first off, I want to mention, besides the rules, there's a quick way to remember your zeros. Now, Ms. Tavalovich is one of our teachers, and this is something early on she'd mentioned to me. This is how I say it to my students. So, rules 2, 3, and 4 can be combined to say tweeners always count, leaders never count, and followers only count if there's a decimal. So this is another way to look at zeros at the beginning, zeros at the end, and zeros in the middle. So if that helps you remember rules 2, 3, and 4, use it. Now, let's look at some quantities and which digits are certain and which digits uncertain and how many significant digits we have. So let's just do a quick review of the ideas here. So let's say I have 14.379 grams. By rule number 1, all of these digits are significant because they're all non-zeros. So this would have a total of 5 significant digits. And my uncertain digit would be that 9. That would be my last significant number. Now in the next one, 6.02, now I've got non-zeros, 2 of them. By rule 1, they always count. And by rule 2, the 0 in the middle counts because zeros between non-zeros always count. So that's why it's 3 significant digits. And my last significant digit would be that 2. That's my uncertain digit. Now the next one, my 1, my 2, my 5, and my 8, all those count by rule 1. Excuse me. Rule 2 says zeros in the... I'm sorry. Let me pause for a second. Okay, I'm back, and I think my coughing fit has passed. So, where we left off, let's go back again. We were on this 120.580. Now, the 1, the 2, the 5, and the 8 by rule 1, all of those were non-zeros. They all have to count, so that gives us at least 4. This is a 0 in between 2 non-zeros, so that's got to count. And that gives us 5. And then last, we have a 0 at the end. Rule 4 says zeros at the end of a number count if there's a decimal. And sure enough, right there is a decimal. So that 0 also has to be significant. And we've got a total of 6 significant digits here. And our last significant digit would be that 0 at the end there. Next one, 7.5 by rule 1. Both of those have to count. That's only got 2 significant digits. Next one, 0.037. Rule 1 says the 3 and the 7 have to count. So I know these 2 are going to count. And rule number 3 says zeros at the beginning of a number never count. So that's why that only has 2 significant digits. And then if we threw a 0 on the end, like we've done at the next one, these are still zeros at the beginning. They never count. Those are still non-zeros. They always count. And by rule 4, this is a 0 at the end with a decimal shown. It has to count. So that would mean 3 significant digits. So that's just a review of what we did for the sig fig rules. So now I want you to try it. So pause the tape here if you're listening to this and go through and try and figure out how many significant digits are in each of the following numbers. So pause it and then go through and try each and then turn the tape on again where we look at the answers. Okay, how many significant digits are each of the following numbers? Well, the first one is going to have 5. The 3 and the 5 count by rule 1. Rule 2 says zeros in the middle always count. Those are zeros in the middle, so they all count. The next one, 3.00. Well, that's going to have 4. 3 counts because of rule 1, and rule 4 says zeros at the end count if there's a decimal, so all of those zeros count. Now the next one, the 3 still counts, but now none of those zeros will count because there is no shown decimal. It's understood where it's at, but it's not shown in the problem, so that only has 1 significant digit. And if I put a decimal at the end, now I've got zeros at the end with a decimal. That would have 4. Next one, scientific notation, don't let it throw you. We're really just looking at the coefficient here, the base number. The times 10 to the third part, that just tells you where the decimal goes. So that's really just placeholder information. These 2 count because they're non-zeros. This is a 0 at the end, and by rule 4, a 0 at the end with a decimal counts. So that's got 3 sig figs. Next one, all those zeros are at the end, and they all count because there's a decimal, so that gives us a total of 5. And the very last one, zeros at the beginning never count. So none of those zeros count by rule number 3. 4 and the 5 count by rule number 1. And rule 4 says zeros at the end count if there's a decimal. Way back here, there is a decimal. So that's got 3 sig figs. And that ends our discussion on the rules we're going to use. And this helps you when you write a measurement to make sure you're writing it with proper significance. And more importantly, when you're reading somebody else's measurement, how you know how many significant digits that you have. And that ends our 4th day of notes on the chapter.